Hello, and welcome to Data Science for Everyone. Today, we're going to explore hypothesis testing, a cornerstone of statistical inference used across science, business, and many other fields. This is part 1 of a 2-part video on hypothesis testing in R. Let's get started. Let's understand why hypothesis testing is important with an example. Imagine a pharmaceutical company has developed a new drug to lower blood pressure. Before bringing it to the market, they need to know, is this drug actually more effective than the current standard treatment? To find out, they run a randomized controlled trial, a study design deeply connected to the ideas of hypothesis testing. Participants are randomly split into 2 groups. One group receives the current drug, that's a control group. The other group gets the new drug, that's the treatment group. After several weeks, researchers compare the average reduction in blood pressure between these 2 groups. How do the researchers know whether the new drug is performing better than the existing drug? This is where hypothesis testing comes in. Using hypothesis testing, we can turn data into evidence for or against a certain claim. In part 1 of the video series on hypothesis testing, we will cover the following topics: one-sample tests, unpaired and paired two-sample tests, and ANOVA tests. Let's start with one-sample tests. Let's look at the salaries dataset that contains the salaries of data professionals to understand hypothesis testing and implementation. To load the salaries data, we use readr's read_CSV function. Using the head function, we quickly view the dataset. The dataset contains a column called job_title, which lists the designation of each individual at the company, along with their salary in USD column that has their compensation in US dollars. We look at a subset whose job title is data scientist. We will be loading the Tidyverse package, and then we filter out the data scientist using the filter function in dplyr and store it in a new variable called salaries_ds. Let's say we assume the average salary for all data scientists is $100,000 US. To test this, we can start by looking at the salary data. The annual salaries are stored in the salaries in USD column. When we calculate the average of a sample, we are getting what's called a point estimate, basically a summary statistic that gives us a single value as an estimate of the population mean. We can calculate this by using the mean function in base R on the salary in USD column. Now, the result we get is different from our original assumption, but the key question is the difference significant? To answer this, we need to generate a bootstrap distribution of sample means. This involves repeatedly resampling our dataset, calculating the mean from each resampling, and compiling those means into a list. A bootstrap distribution is a way to estimate the variability of a statistic, like sample mean, by simulating many possible samples from our original dataset. It helps us understand how much our sample mean might vary just by chance, giving us insight into reliability of our estimate. Let's see how to generate a bootstrap distribution in R. First, we need to create an empty vector called boot_dst. This will hold all the sample means we generate. Then we run a loop 10,000 times. Each time through the loop, we take a random sample from a dataset using the sample_frac function. We set replace equals to true, and this means we are sampling the full dataset with replacement, so the same row can appear more than once in a sample. We calculate the mean of the salary in USD column from each resampled dataset and store that mean in boot_dst vector. After running the loop, boot_dst contains 10,000 different sample means. Together, they form our bootstrap distribution, which we can understand how much the mean salary might vary just by chance. Here is a histogram of the bootstrap distribution. It's bell-shaped, which means that it's roughly normally distributed. Notice that the $100,000 US, indicated with the red vertical line, is on the left of the distribution. The standard deviation of the sample statistics in bootstrap distribution estimates the standard error of the statistic. We calculate the standard error by calling the SD function in base R. The standard error in this case is 5,382. The standard error is the standard deviation of a sampling distribution measuring how much sample statistic, like for example the mean, is expected to vary from sample to sample. Since different variables have different units and scales, it's important to standardize our values before testing the hypothesis. A common way to standardize is to subtract the mean from each value and then divide by the standard deviation. For hypothesis testing, we use a similar approach, but instead of just the mean, we take our sample statistic, subtract the hypothesized value, and then divide by the standard error of the statistic. This calculation gives us a number called the z-score, which tells us how many standard errors our sample statistic is away from the hypothesized value. Let's plug in the numbers we calculated earlier to compute the z-score. The mean annual compensation for data scientists is about $108,187. We subtract this value from the hypothesized value of $100,000, then divide the difference by the standard error. When we do that, we get a z-score of 1.52. This z-score tells us how far our sample mean is from the hypothesized mean, measuring in standard errors. But we don't know yet if this value of 1.52 is a big or a small number, and determining that is the goal of this course. This plot is important to understand z-scores. This is a plot of probability density function for the standard normal distribution. This is a special case of normal distribution with a mean of 0 and standard deviation of 1. It's often called z-distribution because it's the distribution that z-scores follow. Since z-scores tells us how many standard errors a value is from the mean, they map directly onto this curve. We'll be using the z-distribution a lot throughout this course, especially when we are testing hypotheses and calculating probabilities. Hypothesis testing are often like criminal trials. There are two possible states. Either the defendant did commit the crime or they didn't. And there are two possible outcomes. The jury finds the defendant guilty or not guilty. At the start of the trial, we assume that the defendant is not guilty. It is up to the prosecution to present strong enough evidence, called beyond a reasonable doubt, to convince the jury otherwise. In the same way, in hypothesis testing, we start by assuming that the null hypothesis is true, and only reject if the data provides convincing evidence against it. Let's turn to our salaries dataset. One of the variables is job title, which tells us what kind of role a person holds. Another variable is called company size. That tells us how big the company is. For example, small, medium, or large, represented as S, M, and L respectively. Now, suppose previous research suggests that 10% of tech professionals work at small companies. This leads to an interesting question that we can explore using our dataset. Does our dataset provide evidence that greater than 10% of the tech professionals work at small companies? Let's explore this question. Let's start by clarifying some definitions. A hypothesis is a statement about a population parameter, a value we don't know exactly but want to learn about it from our data. In hypothesis testing, we compare two competing ideas. The null hypothesis, called H0, which represents the current or established belief, and the alternative hypothesis, called HA, which represents a new idea that challenges that belief. In our case, the null hypothesis is that 10% of tech professionals work at small companies. The alternative hypothesis is more than 10% of tech professionals work in small companies. Let's go back to our comparison with criminal trial. The defendant can either be guilty or not guilty, and only one of these can be true. At the start, the defendant is assumed to be not guilty. Similarly, in hypothesis testing, we begin by assuming that the null hypothesis is true. We can only change this assumption if the data provides strong enough evidence to reject it. Instead of saying we accept the alternative hypothesis, we say we reject the null hypothesis or fail to reject the null hypothesis. In a trial, if evidence shows beyond a reasonable doubt that the defendant has committed the crime, the verdict is guilty. In hypothesis testing, the equivalent of beyond a reasonable doubt is called the significance level. We'll talk about it later in the video. Let's look at a normal distribution. The tails of a distribution colored in red are the left and right edges of its probability density function, or PDF. Hypothesis tests can help us figure out if the sample statistic fall within these tails of the null distribution. There are three types of tests, and which one we use depend on how the alternative hypothesis is worded. If we are testing for any difference from the hypothesized value, we look for extreme values in both tails and do a two-tailed test. If the alternative hypothesis says something like less or fewer, we perform a left-tailed test. If it says greater or exceeds, we use the right-tailed test. For our hypothesis test, we'll use a right-tailed test because you're looking for extreme values in the right tail. P-values measure how much support is there for the null hypothesis. In other words, they tell us the probability of getting a result, assuming the null hypothesis is true. If the p-value is large, it means that a result is probably not at the extreme ends or tails of the distribution we'd expect under the null hypothesis. So chance could easily explain the result. If p-value is small, it means a result is likely in the tail of the distribution, which makes it less likely to have happened by chance. Since p-values are probability, they'll always fall between 0 and 1. To calculate the p-value, we need to find the z-score. We start by calculating the sample statistic, in this case the proportion of tech professionals who are in small companies labeled as S in the data. This is stored in the prop tech val variable. The null hypothesis gives us the hypothesized value of 10% stored in the prop tech hype variable. Like before, we create a new Bootstrap distribution and store it in an empty list called techboot.tst. Using the Bootstrap data, we calculate the standard error and finally the z-score. Is this z-score of 2.63 significant? Let's find out. To calculate the p-value, we'll pass the z-score to the pnorm function in base R, using the default mean of 0 and standard deviation of 1. Since we're doing the right-tailed test and not a left-tailed one, we calculate p-value by subtracting the result of pnorm from 1. The p-value comes out to be almost 4 out of 1000. Is this value of 0.004 significant? We'll look into this in the next segment. P-values tells us how much evidence we have for the null hypothesis. A large p-value means that there isn't evidence to support the alternative hypothesis. So we stick with the null hypothesis. A small p-value, on the other hand, makes us lean toward the alternative hypothesis and reject the null hypothesis. But how do we decide what counts as a small or a large p-value? What's the cutoff point? The cutoff point is called significance level, denoted by alpha. The right significance level depends on the dataset and the field you're working in. The most common choice is 5%, but 10% and 1% are also widely used. The significance level helps us decide which hypothesis to support. If the p-value is less than or equal to alpha, we reject the null hypothesis. If it's greater, we fail to reject it. It's crucial to choose the significance level before running the test. Otherwise, there's a risk of picking a value that justifies the conclusion we want, rather than following the evidence. Previously, we calculated the p-value to be 0.004. We have set the significance or alpha at 0.05. And since the p-value is less than alpha, we can reject the null hypothesis. We can say that more than 10% of the tech professionals work in small companies. To understand the possible values of a population parameter, we choose a confidence level that is equal to 1 minus the significance level. So if our significance level is 0.05, we use a 95% confidence interval. Here is how we calculate it using the quantile method. The 25% and 75% confidence interval are saved in the lower CI and upper CI variable respectively. This interval gives us a range of values that are likely to include the true population proportion of tech professionals who are working in small companies. Now let's look at different types of errors in hypothesis testing. Let's go back to the criminal analogy. There are 2 possible truth states and 2 possible verdicts, making 4 possible combinations. In 2 of them, the verdict is correct. Those are shown in green and are called true positive and true negative. If they did commit the crime but are found not guilty, they got away with it. Both are errors in justice. These are highlighted in yellow. These are called false positives and false negatives. Hypothesis testing works the same way. There are 2 correct outcomes and 2 types of errors. If we support the alternative hypothesis, when the null hypothesis is actually true, that's a false positive, known as a type 1 error. If we support the null hypothesis when the alternative hypothesis is actually true, that's a false negative, also known as type 2 error. By the way, this table is called a confusion matrix and can be used to calculate parameters like accuracy, precision, and F1 scores. These are beyond the scope of this course. If you want to know more about confusion matrix, please check out supervised modeling and linear regression modeling videos on Python. I have explained them in detail. The links of these videos are in description below. In the case of tech professionals employed in small companies, if our p-value is less than or equal to the significance level and we reject the null hypothesis, there is a chance we made a type 1 error or a false positive. That means we might have concluded that more than 10% of tech professionals work in small companies, when in reality only 10% do. On the other hand, if p-value is greater than the significance level and we fail to reject the null hypothesis, we might have made a type 2 error or a false negative. That means we might have concluded that only 10% of the tech professionals work in small companies, when in fact more than 10% do. In the first part of the video, we looked at z-score, which was a test statistic for one variable. Now let's look at how to compare two variables. A quick detour before I move on to the two sample tests. Looking at the YouTube data, I can see that only 9.3% of you guys have subscribed. That's a lower rate than most p-values we'd ever accept. If you guys enjoyed the video or learned something new, please consider subscribing. It's statistically significant to support this channel. Here we'll explore a related problem, comparing sample statistics between groups based on a certain variable. In the salaries dataset, salary in USD is a numerical variable representing annual compensation. Company size is a categorical variable with three categories: small, medium, and large, represented as S, M, and L respectively, indicating the size of the company. This lets us ask a question. Do large companies pay more to their data scientists compared to the smaller ones? The null hypothesis states that the mean compensation is the same for both large and small companies. The alternative hypothesis states that the mean compensation is higher for those who are working in large companies. We can express these hypotheses using equations. Mu stands for unknown population mean, and we use subscripts to show which group the mean refers to. Another way to write these equations is by comparing the difference between two population means to 0. In this case, 0 represents the assumed difference in means under the null hypothesis. To calculate the summary statistics for each group, we begin with the sample, group it by the categorical variable, and then perform the calculations on the numeric variable. In Tidyverse, this can be done by grouping the data by company size and then taking the mean of the salary in USD column. In this case, larger companies have an average compensation of $103,000, while medium companies pay $126,000 on average. But the key question is this difference statistically significant, or could it be just due to random variation in sample? Even though we don't know the population mean, we can estimate it using the sample mean. We use X bar to represent a sample mean, and the subscripts indicate which group the means come from. The difference between the two sample means serves as a test statistic in our hypothesis test. The z-score we looked at in the first part of the video is an example of standardized test statistic. Z-scores are calculated by taking a sample statistic, subtracting the population parameter it estimates, and then dividing by the standard error. In the case of comparing two samples, the test statistic, denoted as t, follows a similar formula. We take the difference between the sample means of the two groups, subtract the hypothesized difference in population means, and then divide by the standard error. To calculate the standard error, which we need for the denominator of the test statistic formula, bootstrapping is a solid approach. However, there's a simpler way to approximate it. First, we calculate the standard deviation of the numeric variable for each group in the sample, along with the number of observations in each group. Then we plug those values to the standard error formula and compute the approximate result. Here is the test statistic equation again. If we assume the null hypothesis is true, we can simplify it. The null hypothesis states that the population means are equal, which means that the difference is 0. So the population term in the numerator drops out. By inserting our approximation for the standard error, we now have a way to calculate the test statistic using only the values from the sample dataset. We need the mean, standard deviation, and the number of observations for each group to fill the formula for t. We use group by with method combinations for mean, standard deviation, and count. Let's calculate the t statistic. We subset the individual mean, standard deviation, and count parameters and store them separately. Next, we calculate the numerator by subtracting the sample means and the denominator by taking the square root in accordance with the standard error formula. The t-statistic is minus 1.84. Just as with z-scores, we can't draw any conclusions yet. For that, we need to calculate the p-value. Before calculating the p-value for the t-statistic, let's first look at a t-distribution. Just like z-statistics follow a normal distribution, the t-statistic follows what's known as a t-distribution. This type of distribution has a parameter called degrees of freedom, often shortened to df. On this plot, the blue curve shows the probability density function of a t-distribution with just 1 degree of freedom. The red curve shows the PDF or the probability density function of a normal distribution. Take a look at the difference. The t-distribution has thicker or fatter tails than normal distribution. But aside from that, the overall shapes are quite similar. As we increase the degrees of freedom, the t-distribution becomes more similar to the normal distribution. In fact, when the degrees of freedom approach infinity, the t-distribution essentially becomes a normal distribution. Degrees of freedom refer to the maximum number of values in a dataset that can be independently varied. That can be a bit tricky to understand, so let's look at an example. Let's say our dataset has 4 independent observations, and 3 of those observations are 5, 7, and 11. Now suppose we know that the sample mean is 40. With that information, the 4th value cannot vary freely anymore. It has to be 137 to keep the mean at 40. So even though we started with 4 independent observations, knowing the sample mean takes away 1 degree of freedom. We are left with 3 degrees of freedom. In a 2-sample case, the number of degrees of freedom equals to the total number of observations minus 2, because we are using 2 sample statistics, the means of each group. Now let's calculate the p-value for a t-statistic. Recall that we first need to decide on our significance level. We'll set alpha or the significance level to the standard 0.05. We'll also need to compute the degrees of freedom, which is the total number of observations in both groups minus 2. To compute the p-value, we need to use the t-distribution's cumulative distribution function rather than the normal distribution's cumulative distribution function. That's why you'll see pt instead of p-norm. Also notice that the df argument is included. This stands for the degrees of freedom and is essential for t-distribution. We calculate the p-value to be 0.96. This p-value is more than the significant level of 0.05. Therefore, we will fail to reject the null hypothesis and accept that based on the salaries data, the mean compensation are the same for large and medium-sized companies. That was a lot of calculations. Fortunately, there's an easier way to get the p-values quickly. Running a t-test is easy in R. First, we split our dataset into 2 groups based on the company size, keeping only the salary columns. We then use the t-test function to compare the average salaries. We set paired equals to false because the 2 groups are independent. They are different people in different companies. We also set alternative equals to greater to perform a one-tailed test, where we're specifically testing if salaries in large companies are greater than salaries in medium-sized ones. Printing the results, we can see the t-statistic, the p-value, and the degrees of freedom all printed out. Since the p-value is more than our threshold of 0.05, we conclude that there is no statistical difference between the salaries of large companies and salaries of medium companies. If we want a neat table to format the results of the t-test, we want to use the broom package in R. We are going to load the broom package using the library function and then we're going to call tidy on the t-test results. The tidy function prints out a neat table with all the results of the t-test. We can see the p-value is printed as well, which is highlighted in yellow. Previously, we used the t-distribution to compute the p-value for difference in means across two different groups. Now we will look at how to perform statistical tests on paired datasets. Let's bring in our dataset. For this demonstration, we have a modified dataset that contains salaries of data scientists in 2015 and 2025. The goal is to find out whether salaries have significantly increased in 2025 compared to back in 2015. The dataset is in the description below. Now let's form our hypothesis. To find out, we'll set up a hypothesis test. Just like before, the null hypothesis says that our guess is wrong. In this case, the mean salaries is the same for both years. The alternative hypothesis is that the mean salaries are greater in 2025 compared to 2015. We'll use a significance level of 0.05 for this test. Now, there's an important thing to note about this dataset. The salaries from 2015 and 2025 are paired. They come from the same companies. That means they are not independent. So in our model, we need to account for this pairing in the data. Previously, I demonstrated how to run an unpaired t-test in R. Now we'll be running a paired t-test. The syntax is the same. We just need to specify one argument called paired and set it to true. Calling the tidy function, the results are printed the same way as before. As we can see, the p-value is really low. Since the p-value is less than 0.05, we reject our null hypothesis. When performing paired t-tests, always remember to set paired equal to true, since performing an unpaired t-test when our data is paired increases the chances of false negative errors. We have seen how to compare two groups in the unpaired and paired cases. But what if there are more than two groups? Let's look at the original salaries dataset. There's a column named experience level, which contains the experiences of employees such as executive, senior, mid, and entry level, coded as EX, SE, MI, and EN respectively. Suppose we want to find out whether the mean annual compensation varies across different levels of experience. The first step is to visualize distribution using box plots. ggplot's geom boxplot function works well for this. We'll place salary in US on the x-axis and experience level on the y-axis using the salaries dataset. From the plot, we can see that the executives earn a higher compensation than others. But to determine if these differences are statistically significant, we'll need to perform the hypothesis tests. ANOVA tests helps us determine whether there are differences between multiple groups. We start by setting a significance level to 0.005. This is less than what is typically used, but will help us understand the implications on comparing different numbers of groups later on. We use the AOV function from base R to compare values across different experience levels. We specify the formula using the tilde in the middle. The dependent variable is salary in USD, which is on the left of the tilde, and the grouping variable experience_level is on the right of the tilde. We then call the tidy function to print the ANOVA results. The p-value is 2.88 into 10 to the power minus 36. Since this is smaller than our significance or alpha level of 0.005, we conclude that at least two of the experience levels have significantly different compensations. However, this result doesn't tell us which specific categories differ from each other. To determine which categories differ from each other, we have to perform something called a pairwise comparison among the 4 experience level categories. There are 6 possible pairs, which are combinations of 2 categories from 4. So we need to conduct 6 separate tests. We maintain a significance level of 0.005 for these comparisons. To run all these hypothesis tests at once, we use the pairwise.t.tests function in base R. The argument x is used to set the response variable, in this case salary in USD column. G is used to set the grouping argument, in this case the experience level. Setting pool.sd equals to false tells R not to pool the standard deviation across groups. Instead, each pairwise t-test we'll use each group's own standard deviation separately. We'll talk about the p.adjust.method argument shortly. The output is a data frame where each row shows a comparison between two experience levels, labeled as columns group 1 and group 2. We focus on the p-value column, which contains the p-values for each test. 5 of the 6 p-values are below the significance level of 0.005. The one that is above is highlighted in yellow. Although pairwise test seems useful at first, it comes with a major drawback. The more tests we perform, the greater the chance of getting at least one false positive result purely by chance. In this case, we have 4 groups, which leads to 6 pairwise comparisons. As the number of groups increases, the number of comparisons and therefore the number of hypothesis tests grows quadratically. Because each test carries a small chance of producing a false positive, the more tests we run, the higher the overall probability that at least one of them will appear significant just by random chance. With a significance level of 0.005, a single test has a 0.5% chance of a false positive. But with 4 groups and 6 tests, the probability of getting at least one false positive increases from 0.5% to about 3%. If we increase the number of groups to 20, the number of comparisons jumps to 190, and the probability of at least one false positive climbs to over 60%. So as the number of group grows, false positives become increasingly likely, even when there are no real differences. The solution to this problem is to adjust the p-values to reduce the chance of getting false positives. One common method is the Bonferroni correction, which increases the p-values to account for the number of tests being run. To apply the Bonferroni correction, we have to set the p.adjust.method to bonf. R offers several options for adjusting p-values, with some methods being more conservative than others. By default, no adjustment is applied. This is specified with none. However, in most pairwise t-test scenarios, it's better to apply a correction method to account for multiple comparisons and reduce the risk of false positives. The results show the corrected p-values, and we can see that after applying the correction, only 5 of 6 pairs still show statistical significant differences. That brings us to an end of the part 1 of the 2-part video series on hypothesis testing. In the next part, we'll be looking at proportion tests, chi-square tests, and non-parametric tests. So stay tuned. Also, if you have not subscribed, please subscribe to my channel. I plan to bring new videos every week. Also, please like the video if you have learned from it, and comment on what else you guys want me to cover. Thank you and happy coding.